Hello everyone. In this video we're going to wrap up chapter 8 by discussing linear inequalities in one variable. And we learned how to solve linear equations in one variable, and the first thing we needed to learn was two properties, namely the addition property of equality and the multiplication property of equality. If you recall, the addition property of equality mentioned that if you have a equals b with a and b being expressions, then we can add a constant c to both sides without changing the solutions of the equation a equals b. So we have a very similar property for inequalities, basically, which says if you have a less than b, then you can add c to both sides and you will maintain the direction of the inequality and its integrity. So you can, just like in the case of equations, we could say, or equality, we could make this just one property which refers to both adding to both sides and subtracting from both sides, or we could mention them as separate properties. So let's take a look at that possibility. Sometimes it's easier if we list them as separate properties. So for example, we can say the addition property of inequality, right, being if a is less than b, that implying that a plus c is less than b plus c, right? We can also mention the subtraction property of inequality. And notice, of course, we mentioned it for only one inequality sign, but the property will hold for all these other ones as well. So we can say also for this less than or equal to, greater than, or greater than or equal to. So it works with all four of these inequality symbols, right? The subtraction property would just say, look, if you have a is less than b, then that implies that a minus c for some constant c is also less than b minus c. Okay? And in both cases, of course, c belongs to the set of real numbers. All right. Then we have the multiplication property of inequality. Which says the following: if a is less than b, then a times c is going to be less than b times c. And this is where you have to be really careful with inequalities, because that's true only if c is positive. Okay, now it turns out that a times c is going to end up being greater than b times c if c is less than 0. Okay, so, and of course we don't want to multiply both sides of this by 0, because then you would get 0 is less than 0, which is not true. So let's see why this works out this way. Notice that we know that, for example, 2 is less than 5, right? Let me actually make these a little further to the right. So here we have 0, here we have 2, and here we have 5 somewhere, right? Notice that means we would have -2 on this side like that, and -5 like that. So notice we know that 2 is less than 5. That's a true enough statement, correct? Now watch what happens if we multiply both sides by 3, right? So we'd get 2 times 3 is less than 5 times 3, 6 is less than 15. That's true. So notice if you multiply both sides of an inequality by a positive number, the direction of the inequality remains intact. Now, start with 2 is less than 5 again. This time, let's multiply both sides by something like -1. Any negative number will do, but -1 is good enough, right? So -1 times 2, and we want to compare that to -1 times 5, right? Now, notice what happens. On this side, you end up with -2, on that side with -5. But look, -2 is not less than -5. -2 is in fact to the right of -5 and therefore greater than -5. So this will have to change like this. So notice the instant you multiply two sides of an inequality by a negative number, you need to change the direction of the inequality. And that's why we get this property, that if A is less than B, then A times C is greater than B times C if the number you're multiplying on both sides, C, happens to be negative, okay? So that is one of the few things you have to watch out for when it comes to solving inequalities. Multiplying both sides of an inequality by a negative number changes the direction of inequality, okay? And that's that. So of course you could set this up for division as well. And you can say if, let me fit that in here. So you could say if A is less than B, then A divided by C is less than B divided by C, as long as C is positive, and A divided by C is going to be greater than B divided by C if the constant you're dividing by is negative. So it works exactly the same way as multiplication, because remember, after all, division is just, so when you write A divided by C, that's just A times 1 over C, right? So division and multiplication are considered to be equivalent operations. All right. So of course, division is multiplication by the reciprocal, correct? All right, so these are the rules you need to be aware of as we solve inequalities. One other thing that we will need to be really familiar with is the interval notation for representing solutions, because remember, when you solve inequalities, you're usually going to end up with infinitely many solutions, right? So we represent connected subsets of the set of real numbers using what's called the interval notation, which you have seen before, but I just want to remind you. So on the left here, we will look at what are called, finite intervals. And by that, we don't mean the number of points in the interval, we mean finite length. And on the right side here, we'll look at the infinite intervals. And again, here we mean infinite length. All intervals obviously have infinitely many points in them, okay? So just to show you that, consider the small interval from 0 to 1, right? Notice that if I take a number halfway between 0 and 1, I get 1/2, right? If I take the number halfway between 0 and that 1/2 that I just found, it would be 1/4, right? If I take the number halfway between 0 and 1/4, I get what? I get 1/8. So I get 1/2, 1/4, 1/4, 1/8. We can keep going, right? There is no need for this to end, correct? So there you can see that's a quick proof of the fact that there are infinitely many numbers just between 0 and 1 on the number line. The number line is truly a magic land, right? Where interesting things happen. Talk about infinity within finiteness, right? So even though there are infinitely many numbers that can fit inside here, notice that the actual length of the interval, that's easy. To get the length, all I have to do is go 1 minus 0, and I get 1. So notice, infinitely many points contained within an interval whose length is only 1. Now the interesting thing is, I could have done exactly the same thing with the numbers between, say, 0 and 0.1, or even between 0 and 0.01. In other words, pick any two distinct real numbers. The point is that they have to be different, right? Pick any two distinct real numbers and you'll be able to fit infinitely many other real numbers in it. Here's one simple procedure, right? Now you want to see that there are infinitely many numbers between 0 and 1. Here's another easy way. I know that between 0 and 1 there is 0.1, right? There's one real number. There's also 0.11, right? There's also 0.111. Notice those are all different numbers. And then there's 0.1111, right? Etc. Also keep this process going and you'll see that you have infinitely many numbers between 0 and 1 as well, right? And of course there are many other numbers that these processes won't catch, right? So so that's just a quick, because you tell people there are infinitely many numbers in every interval and they're like, what are you talking about, right? This is what that means, okay? All right, so let's look at the finite intervals. So let's say that we want to look at the set of all real numbers between, say, 2 and 5, right? Well, the way we describe that, if we don't want the numbers 2 and 5 to be in that set, we say basically all real numbers between 2 and 5, and that's how where we leave it, right? And notice that that interval can be described using set builder notation as all x belonging to R, such that x, this is kind of the sandwich notation, x is sandwiched between 2 and 5. In other words, x is greater than 2 but simultaneously less than 5, right? That the technical way of saying that is all x, real numbers x, between 2 and 5. Now that's a perfectly good notation. This is called set builder notation. But there's a lot of writing, right? We have a much more efficient way of describing that set, and it's using parentheses and brackets. So what we do is we put, if the number that is at the end, it's called an endpoint. These two are called endpoints. If an endpoint is included in the set we want to look at or describe, then we use a bracket on its side, right? If it is not included, we use a parentheses. So here, an interval is just going to describe the beginning and the ending points. So it starts at 2, ends at 5, and 2 and 5 are not included. So we put 2 comma 5 and we put parentheses on both ends because neither endpoint is included. So we say open interval 2, 5, right? So what if we wanted to look at the numbers between 2 and 5? This time we want to include 2, but we don't want to include 5. In other words, how would we, first of all, notice these lines, that's segments that I'm putting up here, they're actually on the number line. I'm just putting them a little further up so it's easier to see what set we're looking at, right? So otherwise, these numbers are here on the number line. So here we're looking at all numbers between 2 and 5, and since we want to include the 2, we say all real numbers between 2 and 5 left inclusive, right? That means include the left endpoint but not the right one. So notice that the set builder notation for this will be all x belonging to R, such that the only thing that's going to change here is the first inequality is going to turn into less than or equal to. When it's just less than, that's called a strict inequality. This is a non-strict inequality. So we get 2 less than or equal to x, less than 5. Notice the inequality on the right side doesn't change because we still don't want 5 to be included in the set we're considering. Notice that the interval notation here will be bracket because 2 is included. When you want to include an endpoint, use a bracket. When you want to exclude it, use a parenthesis. So we put 2 comma 5, and we don't want 5 included, so we put a parenthesis on the right of 5. Okay? Then we have the possibility that maybe 2 is not included, but 5 is included, right? So if we want to look at all real numbers between 2 and 5, including 5, excluding 2, right? The way we say that, technically, we say all real numbers between 2 and 5, right inclusive, right? That means include the right endpoint 5, exclude the left endpoint 2, right? So the way we would describe this set, it would be very similar again. So all x belonging to R such that, think about what would change, pause the video, and then come back, see if you had it right. All right, so welcome back. I think you'll agree that all we need to change here is change the second less than to less than or equal to, correct? All right, so in interval format, again, pause the video, write it down, then come back and see if we have the same thing. All right, I think you'll agree that this time we would have parentheses 2 comma 5 and then bracket, right? All right, so the last case of a finite interval, notice, by the way, the length of each of these intervals is 3, right? So when we say finite, we're talking about that length, right? Now, if we were dealing with general numbers a and b, of course, the length would have been b minus a, right? So with no loss of generality, we can just use 2 and 5 because you can connect to that more easily. All right, so what if we want to include both 2 and 5 and all numbers between them, right? So this time we say all real numbers between 2 and 5, comma, inclusive, right? So that means including both endpoints, all right? So notice that that's all x belonging to R such that 2 is less than or equal to x, less than or equal to 5. Notice this time both inequalities turn into their non-strict version, right? Because you're going to be including the endpoint. So here we say closed interval to 5. So this is a closed interval, and that's an open interval. So what do we call these two? Well, we could have called them either half open or half closed, right? Well, we decided universally to go ahead and refer to them as half open. So these two would be half open intervals. That's an open interval, and that's a closed interval, okay? So basically, an interval is a unbroken piece of the set of real numbers is what it is, right? So what about the infinite intervals? Well, we have maybe the possibility that we want to look at all real numbers, say, less than 2. So let me make that smaller. What about this set, right? Notice in set builder notation, that would just be all x such that x is less than 2, right? Much simpler. And this in interval notation, well, remember, the interval, the way we write it is where does it start, comma, where does it end? Well, where does this interval start? It doesn't, right? It has no beginning. So we indicate beginninglessness using negative infinity. Notice I didn't put it on the number line because the negative infinity is not a number. It's a numerical concept. It just tells us, it describes beginninglessness, right? So we put negative infinity, and we always use a parenthesis next to that because remember, it's not a number that we can include, right? And then we put comma. It does end at 2, and 2 is not included, so we need a parenthesis. Notice this would be considered an open interval, okay? So that's so when we say this interval is infinite, we're talking about the length, because remember the length of this interval is infinite, right? Because it has, you know, it keeps going in this direction forever. So what's the length? There is no finite number you can use as the length, right? So the length is infinite. What about if we want to consider all real numbers greater than 2, right? That looks like that, right? So basically this time we're looking at all x such that x is greater than 2, right? And so this time this interval has a beginning but no end. So how do we indicate endlessness? With positive infinity, right? So we say parentheses 2 comma infinity. Again, you always use a parentheses to the right of infinity or to the left of negative infinity, because you can't include those. They're not actual numbers that you can include, so you never want to put a bracket next to those. All right, then what if you have all real numbers that are less than or equal to 2, like that, right? So that's all x such that x is less than or equal to 2. And this time we put negative infinity comma 2, and of course bracket because we want to include the 2, right? The last case is when you have all real numbers greater than or equal to 2. So of course in set builder notation it's just all x. Notice that I'm being a little informal here. I should say x belonging to R. I was running out of space here, so I left that out, but we're assuming we're only dealing with real numbers anyway, right? So a lot of times you'll see this belonging to R left out, but when it is clear from context that we're only dealing with real numbers, as we are in this class, right? So all x belonging to R such that x is greater than or equal to 2, right? And pause the video, write down what this would look like as an interval, then come back and check. All right, so I'm hoping you got bracket 2 comma infinity and then close the parentheses. Okay, now these are the finite intervals as well as the infinite intervals that we will encounter as solution sets to the inequalities that we're going to solve. Make sure you understand these before we proceed. The kinds of inequalities that we're going to be interested in solving are the linear variety that can be put into this form, right? Notice that any of the inequality symbols may exist in the particular inequality we're solving, right? And of course, we don't want m to become a 0, because then we lose the variable term, and then it's not really that interesting as far as solving goes, right? All right, so here's a very simple inequality that we can solve. So we have 2x minus 3 is less than 7. And here we can go ahead and remember, we treat these exactly like equations with two exceptions. One, remember, multiplying or dividing both sides by a negative number changes the direction. So this is a mandatory change that must occur. And here's a recommendation. You know how with equations, when we're trying to solve them, we simplify, remember, both sides, then we separate, and finally solve. Notice in this step, in the separation step, when it comes to equations, we can go either way. We can take our variables to the left side and constants to the right, or other way around, right? Well, with inequalities, you can do that too, but because it's easier to interpret if the variables are on the left side, when it comes to inequalities, the recommendation is at the separation phase, always move the variable terms to the left side. All right, some people have the habit of doing that even with equation, right? With equations, but with equations, it really is easier to go with wherever the larger coefficient is, right? But in this case, with inequalities, we won't care about the size of the coefficients. We'll always move the variables to the left side. So here, there is nothing to simplify, right? So we're ready to separate, right? So we're going to go ahead and add 3 to both sides, which means you can move the -3 to the other side. Remember, adding or subtracting from both sides of an inequality does not change the direction, right? So you know how you can change sides, change signs with equations? You can do that with inequalities as well. And you never change the direction of the inequality by simply adding or subtracting from both sides. So here we're just going to get 2x less than 7 plus 3. So 2x less than 10. And we get x is, now notice we're going to divide both sides by what? By 2, right? Notice that's a positive number, so there is no need to change directions, right? So we end up with x is less than 5. So now we can write the solution set. In set builder notation, it'll be all x such that x is less than 5. In interval notation, it's easier if you graph it first, then write the interval notation. See? There is all the real numbers less than 5, right? So where does this set begin? Notice it has no beginning, so we're going to use -infinity, comma, where does it end? 5. Is 5 included? No. Therefore, we put parentheses after it. That's it. So we just solved this inequality, and you just need to know how to present your solution properly using intervals, and also need to know how to graph your solution sets. And notice there are infinitely many numbers here that will satisfy this equation. You can do a test point just to verify, right? So think of any number less than 5. Anytime 0 is a possibility, that's a great number to use because it's so easy to work with. Notice 0 falls in here somewhere. So plug in 0, right? What do you get? You get 2 times 0, which is 0 minus 3. That's -3. Is -3 less than 7? It sure is, okay? And notice that it becomes true. You can also pick any number really close to 5 as well, and it'll still work, like 4, right? 2 times 4 is 8, minus 3 is 5, which is again less than 7. So we just verified the fact that these are the solutions, all real numbers less than 5 for 2 numbers, 0 and 4, right? You can plug in any number less than 5, and that number, when plugged in here for x, will satisfy this inequality and make it true. Therefore, it's a solution, okay? All right, so here we're looking at another inequality which we're going to solve. Notice that the same 3 steps are involved. Simplify both sides, then separate the variables from the constants, and then go ahead and solve, right? So now there's no simplification needed on either side, right? There's no like terms you can combine. We're ready to separate, but remember here we're always going to move the variables to the left side when we're dealing with inequalities. It'll make the interpretation of what the solution is much easier. So here we're going to have 2x minus 6x greater than. Notice if this were an equation, we would have probably moved that to the other side because that's the larger coefficient. But with inequalities, don't care about that. Always just move your variables to the left side. So here we get 3. Notice the -5 moves to the other side, becomes 5 because we're adding 5 to both sides, right? And here we end up with -4x is greater than 8. Now we're about to divide both sides by -4, right? Don't do that on the same line. Go to a new line. write your inequality, go ahead and divide by -4, and immediately, as soon as you do that, because you're dividing by a negative, change the direction of the inequality. That's simple, okay? So you end up with x is less than -2, okay? And now we're going to write the solution set as all x such that x is less than -2. To make sure you write the correct interval notation, graph it first. We have -2, and we're interested in all real numbers less than that. So the real numbers less than that are going to be to its left, right? So we write parentheses, -infinity, comma, -2, like so. Okay, so don't forget that when you divide both sides of an inequality by a negative number, that's going to change the direction of the inequality instantly, okay? And also make sure you can graph it on the number line. Now, in homework systems such as my MATLAB, etc., or Math Excel, notice that this arrow will actually be on the line, usually with a different color. So let me show you what that may look like. It'll look like this. See, just with a different color. And sometimes, well, especially in Pearson systems, they do this. Instead of putting an open circle, they put a parentheses just to make it look more like, you know, this notation. Now, personally, and from the standpoint of most mathematicians, the preferred notation is the open circle and then arrow to the left like that. So, but you should be familiar with this. In case you see that, you need to recognize that. It's the same thing, right? So this graph is describing this same graph that we have been learning how to do. We will always be doing this when we do the work together, but do realize that they are the same thing, okay? All right, so here's another inequality where there is a little bit of something we need to do on one side first before we separate, right? So notice that we can go ahead and distribute that 3 on the left side, right? So we get 3x minus 6 less than 5x minus 3. And of course, we're going through our 3 steps: simplify, separate, solve, right? So notice that we're done simplifying. We're going to go ahead and separate. Remember, at this phase, we always move the variable terms to the left side. 3x minus 5x less than, and move the constants to the other side, to the right side. So we have -3, which doesn't change sign because it's already on the right side. But we move the -6 to the other side by adding 6 to both sides. That changes sign, becomes +6. So we get -2x less than 6, right? Sorry, 3. So now we divide both sides by -3 by -2. Now be very careful. The instant we do that, we have to change the direction of the inequality, right? So that's why I do it in a new line so that I can change the direction, all right? Usually with equations, we take care of the dividing on that same step. Don't do that with inequalities. Go to a new line, it's safer. So we end up with x is greater than -3/2, right? Let's take a quick look at what that looks like. So here we have -3/2 greater than that. So we want open interval, arrow to the right. That's where the numbers larger than -3/2 reside on the number line, right? So the solution set, basically in set builder notation, all x belonging to R such that x is greater than -3/2. And in interval notation, parentheses, -3/2, comma, infinity. Okay, and parentheses because it's a strict inequality, so the endpoint here is not included. If it were included, if this were filled in and this were greater than or equal to, we would just turn this parentheses into a bracket. That's all. In fact, if this were 3 times x minus 2 less than or equal to 5x minus 3, all the steps would look the same, except at the end we would end up with x greater than or equal to negative 3 halves. So the graph would have had a filled in or closed circle and then arrow to the right. Solution set would look like all x belonging to R such that x is greater than or equal to negative 3 half in set builder notation, and in interval notation it would be bracket negative 3 halves comma infinity. Okay, so this were a what if scenario. The actual problem we're dealing with actually has a strict inequality. Okay, so that would be the solution for the actual problem we were dealing with on this page. Okay, once you take statistics next term, you'll find a lot of expressions such as this that you'll encounter. So, and this is actually placing a boundary on the variable mu. Okay, so which, as you know, stands for population mean. So here we want to substitute certain values and find an inequality which tells us the restrictions on mu. We're going to substitute 20.3 for x bar, okay, 1.708 for t, and 7.6 for s, and 28 for n in this compound inequality to get the boundaries for mu. So let's see what we get. So notice here we get 20.3. Let me bring the original back over so you can see it. Okay, so notice we're just plugging 20.3 for x bar right there, 1.78 for t, right, and then 7.6 for s right here, see, and 28 for n, so square root of 28. And we do the same thing on the right side, right? The only difference is we have a plus here, minus here. We evaluate this on a calculator as well as this, and we get mu is going to be between 17.8 and 22.8. And here's a graph of the solution set for mu in this scenario, okay? So very simple, you're just plugging in, just have to be careful and make sure you plug in correctly, and especially into the calculator correctly. Next, we want to take a look at what's called a three-part inequality, which looks like this. Notice this is actually two inequalities lumped into one. We call it a compound inequality. What I'm painting here in red, that's one of the inequalities. And what I will show with red is the other inequality. In other words, you can actually rewrite this inequality like this. Negative 5 is less than 2x minus 1, and that's the connector. 2x minus 1 is less than 7. So notice that's two inequalities, but because the steps for solving it are going to be the same, we're going to solve the two inequalities simultaneously. So we keep our attention on x. We realize that we need to get x by itself first, the x term, right? And that is going to require us to get rid of that negative 1. How can we get rid of negative 1? Well, by adding 1, right? So that's what we're going to do. Now remember, this is a three-part inequality. So whatever you do to one part, you have to do to all three parts. So I'm going to add 1 here and add 1 there as well, okay? This is basically saying, look, what are you going to do if you want to get rid of that negative 1? Add 1, right? So add 1 like that, and on the same on this other inequality, right? Notice we're just showing that we're doing both of those operations simultaneously here. So we end up with -4 less than 2x less than 8, right? When we combine them, we get 8. And it's exactly what's going on up there as well. -4 is less than 2x, and 2x is less than 8, right? What would we do next? We would divide both sides of each of these inequalities by 2, right? And because 2 is positive, no need to change direction. And that's exactly what we're going to do here as well. So we're going to get rid of that 2 like so. And because we are dealing with a 3-part inequality, we have to do that to all 3 sides. And of course, because up here, when we do this, we also have to do this, right? And we end up with x being between -2 and 2. Notice up here, this one would give us a -2 is less than x, and this next inequality here would give us x is less than 4. Okay, we had an error here. That's a 4, not a 2. And x is less than 4. 8 divided by 2 is 4. I had inadvertently written 2, so make sure you correct that if you're following along. That should be a 4. So basically, the solution set is going to be all real numbers between -2 and 4, right? So let's take a look at the graph of that. Here's -2, here is 4. Open circle on both, of course, because neither endpoint is included. So again, we can write the solution set in set builder notation as all x belonging to R such that -2 is less than x is less than 4. Or we can use the much more efficient interval notation and just write parentheses -2 comma 4, like so. And both notations are correct, except this is just a compact form of that. So this set and this set are exactly the same. And remember, we're using parentheses here in a very different manner from what you may be used to as the way we use them in ordered pairs on the Cartesian coordinate plane. Those were referring to points in the plane. These are not points in the plane. These are connected subsets of the set of real numbers. Okay, so don't confuse this notation for an ordered pair. And remember, for example, when it came to ordered pairs, 4, -2 was a perfectly good ordered pair, right? But it is a completely nonsensical statement when it comes to intervals, because with intervals, remember, the left endpoint is always less than the right endpoint, right? So this would be impossible, because this would be a nonsense interval, because you can't have the left value larger than the right value. So this could be an ordered pair, but it could never be a what? An interval, right? All right, so there is how you would solve a 3-part inequality. Whatever you do to one part, do it to all 3 parts, and it's very, very simple, okay? All right. So before we go away from this problem, there is a way to check this using graphing, which is kind of neat. And let's take a look at that before we go away. So in order to verify this using graphing, what we're going to do is we're going to look at the inequality -5 less than 2x minus 1 less than 7, the original inequality, right? And we're going to go ahead and call each of the pieces y and graph. So in other words, this one graph will be that part being set equal to y. The next one will be this part, so y equals 2x minus 1, and the last one will be y equals 7 for this part, right? So we go ahead and graph all 3 of those functions. So we have y equals -5, and we have y equals 2x minus 1, and we have y equals 7. All right, so notice that when y values are between -5 down here and 7 up here, right? So the -5, remember, is just going to be a horizontal line going through y equals -5, and the y equals 7 is going to be a horizontal line going through y equals 7. Notice that when y values on this graph, the oblique line, are between -5 and 7, the x values are going to be between this point, this x value, -2, and the x value for that point, which is 4. See? So x between -2 and 4. So that's a nice way of verifying that we've done this correctly graphically. So when y values are between -5 and 7, we can see the x values are between -2 and 4. Okay? That's how you would verify it graphically. All right, for the last example in this lesson, we're going to look at an application. Digital music revenues in the United States are shown in this table for various years, and let R be the annual revenue in billions of dollars. So this means $1.86 billion, right? At T years since 2000. So when we set up our table, we're going to set it up with T not representing these numbers, but for example, for 2006, we would use T equals 6, right? We would subtract 2000 from each to get the corresponding T value, right? Like this, right? So we can see the next would be 10, and then 12, 13, like that. And then we can make a scatter plot, and then we can see if there's a model that comes close to it. Let's take a look at that. Okay, so here I've gone ahead and plotted these points. As you can see, T equals starting with 6, working all the way up to 13. That'll be the explanatory variable. The response variable here, the annual revenue, starting with 1.86, going up to 4.36 billion. And it turns out that if we look on the next page here, this is a good model. As you can see, I've graphed it here. Of course, instead of R and T, I used Y and X because that's how these calculators work. So, but notice that model is a very good model that comes very close to all of those points, right? In fact, some of the points fall right on it. So now we can answer some questions regarding this model. Notice that what we want to do here is estimate when the annual revenue was more than 3.7 billion. Now recall that this expression right here is given the revenue, right? So all we have to do is form an inequality of this type. 0.34t minus 0.11 greater than 3.7. So here we could clear the decimals, or we could just work with them. With decimals, if you're comfortable enough, it's usually quicker just to work with them. So we'll keep the 0.34t here, move the negative 0.11 to the other side, so we get 3.7 plus 0.11. So we get 0.34t is greater than 3.81. Now we divide both sides by 0.34. Given that 0.34 is positive, we don't need to worry about switching directions or anything, and I can go ahead and just do the division right there. If I'm dividing by a negative number, I always do it in a new line so that I can flip the inequality in that new line. But here I'm dividing by a positive number, so I don't need to worry about that. And we end up with t is greater than, now we just need to figure out what 3.81 divided by 0.34 is. So we'll just do the division. 3.81 divided by 0.34, and we end up with 11.2, so approximately 11, right? So we can say 11.2. Now remember, t needs to be added to the year 2000. So if we just estimate that to be around 11, we get the year would have to be greater than 2011, right? So for years after 2011, that's when the annual revenue was more than 3.7 billion. Now, that said, if you look at the graph again, or the table even, let's take a look at that. Note that we only have data up to 2013. So if we try to make predictions outside of this range, meaning above, later than 2013 or earlier than 2006, if you recall, that's called extrapolation. That means trying to find an estimate for a zone outside of your given data, right? So therefore, we don't have much faith in any prediction the model would make after 2013. Okay, just keep that in mind. And that pretty much brings us to the end of this lesson. And now we'll just take a look at a few problems from the homework assignment, and that should cover this section. All right, so here we're looking at a very simple problem, but sometimes it's the simple ones that can get you, right? So let's make sure we can handle that. So notice that here we're dealing with negative x less than 11. So do note the fact that we're not solving for negative x, we're solving for x. So we need to get rid of that negative 1. How do we do that? We divide or multiply both sides by negative 1. Remember, when it comes to negative 1, dividing or multiplying by negative 1 has the same effect. So might as well go ahead and multiply. Now remember, we're multiplying both sides of an inequality by a negative number. So that means we immediately switch the direction, okay? And we end up with x is greater than negative 11, okay? And now we can write the solution set, but let's do a graph quickly first. Notice negative 11, x greater than that would look like that, right? So it's all x belonging to R such that x is greater than negative 11. That's the set builder notation version of the solution set. And for the interval notation, we're just going to start at negative 11. So parentheses negative 11, and we're not going to stop, right? So greater than, comma, infinity. And of course, always parentheses after infinity. Why parentheses on the left side? Because negative 11 is not included. That's what we call a strict inequality. Remember, this and this, they're called strict inequalities. All right, that's that. What if we're dealing with a fractional situation like this? If this were an equation, you know that my preference is for you to handle it like a proportion, right? When it comes to inequalities, it's better just to multiply both sides by the reciprocal of that number. So we start with negative 4/5 x is greater than or equal to 4. We're going to multiply both sides by the reciprocal of negative 4/5, which is of course negative 5/4, right? So negative 5/4 times the left side, which is negative 4/5 x, and negative 5 4 times the right side. Now we do note that the number being multiplied on both sides is negative, so you know that you immediately want to switch that direction. So it becomes less than or equal to. Anytime you multiply both sides of an inequality by a negative number, immediately change the direction of the inequality, okay? So we notice, of course, on this side, they all cancel out. And on this side, those two cancel out. So we end up with x. And of course, negative times negative is positive. So we just get positive 1x, which is just x, less than or equal to negative 5. Now, a quick sketch of the solution set will show us we have a closed circle, an arrow to the left, because that's where the real numbers less than or equal to negative 5 reside, right? So the solution set in set builder notation will be all x belonging to R such that x is less than or equal to negative 5. And in interval notation, notice this set has no beginning. We indicate that using parentheses negative infinity, but it does have an end at negative 5. And negative 5 is included, right? Greater than or equal to means, or here, less than or equal to negative 5 indicates that the solution is any number that's less than negative 5 or equal to negative 5. So negative 5 is included, so we put a bracket. And that's that. All right, so here we have an inequality where there is some simplification possible on both sides first. So we always simplify both sides first before we move things around. So we distribute the 4 here and we distribute the 3 there. So we get 20x minus 8. If you think you should be able to handle any problem, stop the video and try it, then come back. So 15x plus 6, right? So now we have 20x minus 15x greater than or equal to 6 plus 8. Notice after we distributed, there was nothing else to do on either side, so we separated. Move the 15x to this side, became negative 15x. Move the negative 8 to that side, became positive 8. Of course, basically, if you want to see what we're actually doing, we are adding 8 to both sides. We're also subtracting 15x from both sides. So in case you like to show that step, you could do that too. All right, so there we are. So we did that at the same, we did both of those simultaneously and we end up with this. So we get 5x is greater than or equal to 14. Now we divide both sides by 5. And of course, we don't need to change the direction because we're dividing by a positive number. So we get x is greater than or equal to 14 over 5. If we take a look at that solution set, on the number line, we mark 14 over 5. Now, keep in mind, in computer algebra systems, they're going to not show you 14 over 5 on the number line. So you'll need to know what that number is as a mixed number. So just divide, right? We know that we get 2, 10, 4, right? So, and don't forget that loop, right? So 2 and 4 fifths, right? Starting here, 2 and this number over that number. So also, so look for that, but they won't show you 2 and 4 fifths either. They'll show you some number between 2 and 3. and they'll make sure that it's much closer to 3 than it is to 2. So they'll put it somewhere around there. Okay, so make sure you know the mixed number equivalent of a number like this. Okay, like 14/5. So anyway, we have that. So we have a full circle because it's greater than or equal to, so 14/5 is also a solution, and so is every number greater than 14/5. So we go ahead and do that. Right now, you want to get a quick check. You could always plug in a number like 3 and make sure that it makes it true. See, that's 5 times 3 is 15, minus 2 is 13, times 4 is 52. On this side, we have 5 times 3, which is 15, plus 2 is 17, times 3 is 51. And 52 is greater than or equal to 51, so it makes it true. That's just one quick example to show you how you could do a test point to make sure you've done it correctly, okay? And that's that. All right, so here we have an inequality containing some fractions. So what we're going to do is go ahead and find the LCD first, and then we'll multiply both sides by that LCD. So if you recall from dealing with equations that have fractions in them, we are going to go ahead and for a problem like this containing fractions on both sides, we're going to find the LCD of all the fractions, which of course in this case is pretty simple. It's just 15. And we're going to multiply it on both sides according to the multiplication property of inequality, right? So we end up with 15 times the left side equals 15 times the right side. Now, we do need to, of course, distribute, correct? Like so. Now, 15 is positive. We don't need to worry about changing the direction of the inequality or anything like that, but we still need to distribute. So we get 15 times negative 1/3 x. Now, positive 15 times negative is going to give us negative 15 times 13/15, greater than or equal to 15 times 1/5 plus 15 times 4/3 x right there. All right, so we will go ahead and cross cancel as much as we can. The 3 and the 15 leave us 5 here. The 15s cancel out. Don't worry about the sign for now. We'll take care of it in the next step. 5 and 15 leave us 3. 3 and 15 leave us 5 here. So carefully now, we notice that we have the sign here will be negative. Positive times negative is negative. And all we have left is 5x. In the next term, we notice that we have negative 13. That's it. Greater than or equal to, on this side, we have 3 plus 5 times 4 times x, right? Which is 20x, right? So now remember, at the separation phase, we always take all variables to the left side. So negative 5x minus 20x greater than or equal to 3. We move the negative 13 to the right side, so it becomes positive 13. So on the left side, we have negative 25x greater than or equal to, on the right side, we have 16. Now we're going to divide both sides by negative 25. Since I'm dividing by a negative number, I'm going to do it in a new line. I'm going to put negative 25 on both sides. And of course, I'm immediately going to change the direction of the inequality because I'm dividing by a negative, right? So we end up with x less than or equal to negative 16/25. So notice that if we were to graph it, we'd have negative 16 over 25, full circle because it's included, and less than or equal to means arrow to the left. So now we can write the solution set. So the solution set is going to be all x belonging to R such that x is less than or equal to negative 16 over 25. And that's set builder notation. In interval notation, where does this interval begin? It has no beginning. How do we indicate that? Using parentheses negative infinity. And where does it end? It ends at negative 16 over 25. And that's it. We're going to have to use a bracket because we want negative 16 to be included. And that's it. Just make sure that you use that bracket, not parentheses. All right, so that's a good one, right? Just a quick note on this one. Again, if this were an equation, you know I prefer for you to solve it by cross multiplying. Stay away from cross multiplying with inequalities. Just go ahead and multiply both sides by 30. In other words, find the LCD, multiply both sides by the LCD, and take it from there, okay? The rest will be pretty easy. You can handle that. All right, so here we have a three-part inequality. And remember, with three-part inequalities, whenever you do something to one part, you have to do that to all parts, right? So notice that the first thing we want to do is clear the fractions, right? We notice the LCD for all the fractions in the entire problem is 4. So we're going to go ahead and multiply all three parts by 4. So we end up with 4 times 1/4 less than or equal to 4 times 6 minus 3/4 x less than 4 times 3. Notice that we're not going to be changing the direction because we're multiplying by a positive number, right? So all directions remain the same. So we cross cancel now. We notice that those cancel out. And we end up with, let's go ahead and distribute the middle part. So 1 less than or equal to 4 times 6 minus 4 times 3/4 x less than 12, right? Again, we can cross cancel here. So we have 1 less than or equal to 24 minus 3x less than 12. Notice that now we want to isolate the negative 3x first. So we go ahead and get rid of the 24 by subtracting it from all three parts. You do something to one part, you have to do it to all three parts. Remember that, with three-part inequalities. So now we get negative 23 less than or equal to negative 3x less than negative 12. And now we'll go ahead and divide all three parts by negative 3. I'm going to go do that in a new line. Remember, anytime we divide by a negative, we do it in a new line. You know why, right? Because we immediately need to change all the directions. So that becomes greater, the first one becomes greater than or equal to, second one becomes greater than, okay? So we end up with, let me move this up a little bit. Okay, like so. All right, so we end up with, notice negative divided by negative is positive. So 23 over 3 greater than or equal to x greater than negative 12 divided by negative 3. That's just positive 4. Now, even though this is correct, it'll be a lot easier if you actually write from smaller to the largest. So we can write the equivalent of this three-part inequality starting with 4. So we say 4 is actually less than x, and then less than or equal to 23 over 3. So now we know that on the number line, we're going to have 4 and 23 over 3. Note that if we do the long division, we get 23 divided by 3. That gives us 7, 21 with a remainder of 2. So 7 and 2/3. So you're going to want to look for that in homework systems, okay? And notice that we have a strict inequality on this side, so 4 is not included, so that'll be an open circle. And we have less than or equal to on this side, so that means 23 over 3 is one of the solutions. And then, of course, everything in between, right? So we're going to write the solution set as all x belonging to R such that 4 is less than x, less than or equal to 23 over 3 in set builder notation, and in interval notation we're going to put parentheses 4 because 4 is not included, comma 23 over 3, and then bracket because 23 over 3 is included in this interval, okay, of a solution set. So there you go. That's how you would handle a problem like that one. All right, and that should bring us to the end of our lesson for today. That should be enough to get you through the homework, so make sure you get it done on time and stay safe until our next video.